their formation. In particular, for volatile molecules, it's the temperature at the formation distance. And as planetary astronomer, I generally think of volatiles as things like water and more volatile than that. So the classical small body paradigm is that asteroids are those objects that formed in the inner solar system up to and perhaps just on the other side of the water snow line. However, comets are objects that have formed well beyond that, and we need that in order so that they can accrete carbon dioxide, carbon monoxide, all these other more volatile molecules. So to give you kind of a working definition of what's a comet, what's an asteroid, which is kind of important for this talk, what I would say a comet is an object that is driven, has mass loss driven by ice sublimation. From that sublimation, we have, it produces a coma. This is a gas coma in green. There's a dust coma buried within that in white light. And we get a tail from solar radiation pressure accelerating that dust. In contrast, an asteroid does not have those ices in this classical definition, and it would be inert. However, that's not 100% true, or I wouldn't say that asteroids are completely devoid of volatiles. Some asteroids do have volatiles, but they're in the form of hydrated minerals. They're not in the form of ices. So in the contemporary solar system, all these gray dots are asteroids, and a lot of them are located between the orbits of Mars and Jupiter in the quasi-stable part of the solar system, or a very stable part of the solar system, dynamically stable. But asteroids leak out of this and come into the inner solar system and become the near-Earth asteroid population. In contrast, the comets here are in the light blue circles. They are dynamically separated, and they originate from the outer solar system. And this was the broad brushstrokes of small body science. However, what we now know of and what's been discovered in the last 20 years is a small handful of objects. There's these green circles in here within the asteroid belt that behave as comets. El Bizarro here on the right is an example of one. It produces dust. It has a long tail. However, dynamically, it's indistinguishable from any asteroid in the main belt. And here's a sample of those objects. So they all have the appearances of comets. They have dusty comae tails and repeated mass loss near perihelion. So everything's telling us about these objects is they likely have some kind of ice on them that's driving their mass loss. But despite all the searches for any kind of gas, nothing has been spectroscopically identified. So how would you go about identifying the driver of activity in a typical comet? And I'm partial to the near-infrared wavelength region, although there's other ways to do this. But I'd say the near-infrared is a key wavelength regime for just many aspects of cometary comae. First of all, here's looking at just starting with the continuum. We have scattered sunlight on the short wavelengths and thermal emission on the long wavelengths. This plot happens to be reflectance versus wavelength. The top plot is a spectrum of Hartley 2. These are both spectra of Hartley 2, but just two different samples within the coma from the Deep Impact spacecraft. The top one is a more dust-dominated spectrum. The bottom one has ice features in it, 1.5, 2, and 3 microns. The 3 micron band is, in this image, appears to be dominated by water ice. However, there are other explanations for that in some other objects. I'm not going to talk much about the continuum. If you want to know more, also see the talk on Comet Hale-Bopp in this session by Cyril Opiton. So, but looking at the volatiles, the great thing about the near infrared is that we have the three most abundant volatiles in comets, water, carbon dioxide, and carbon monoxide, all have strong or relatively strong emission bands. The water is at 2.7 here in Hartley 2. You can see it, a nice band there, 2.7, CO2 at 4.3, and carbon monoxide would be at 4.7. However, this happens to be a CO-depleted comet, and it just is not detected in the spectrum. There are other emission bands from other species. They're better studied at higher spectral resolution than this. If you want to know more about cometary spectra with JWST, also see posters by Silvia Protopapa et al. And Olga Harrington et al. So here's the dusty spectrum of comet Hartley 2. It's now in more typical spectral units where we have its flux density, spectral flux density units versus wavelength. So we have scattered sunlight rising on the short wavelength side, thermal emission on the other, and the prominent water and CO2 bands. Now, as I said, this is a key wavelength range for determining the composition of comets. So what we need is a space observatory that has sensitivity and low resolution spectroscopy from those over these wavelengths, which we do have with JWST and NIRSPEC. So given that, we looked at the population of these main belt comets to determine which ones were observable by JWST and which ones were likely to be active when JWST pointed at it. And there was one object in this cycle, and that's 238P Reed, and here's our spectrum of it. In black. And right there at 2.7 microns, that's the first direct evidence for any volatile in this population of water gas here. But this data is more than just a water detection. It's also a CO2 non-detection, and this is very important. Over here at 4.3 microns, there's a little bit of noise here, and in a subsequent spectrum, I've been able to address that much more carefully, but all I have for this talk is the preliminary spectrum. The upper limit, there's a non-detection of CO2 at that spot, and the upper limit in the CO2 to water ratio is 2%. And it's a 3 sigma upper limit, and I think that's a little bit generous, and we'll do better for our final publication. So what does that mean in the cometary population? Well, this is a plot from a literature review of CO2 to water, and you see it also includes a discussion of carbon monoxide, but this is by Harrington Pinto et al. And we're showing all the CO2 to water ratios measured in comets as a function of heliocentric distance. And there's a slope to this data that's likely has something to do with how comets work and how volatile CO2 is versus how volatile. CO2 is a more volatile molecule, so it can be active at higher heliocentric distances. But exactly why that particular slope exists, I don't think that we really know just yet. However, what's important here is this blue arrow that I've indicated. That's our upper limit for main belt comet 238P Reed, and it is a strong outlier from that trend. So this is a unique part of this plot. It's the lowest CO2 to water ratio that has been measured in that context. Now, that CO2 to water ratio, because of the different volatility of the two ices, this is really we like to think of it as a temperature gauge. Something about this comet is warm with respect to the more typical cometary population. Now, what we don't know is what that precisely means in terms of whether it formed in a warmer location than all the other comets, or had it been a normal comet in its early history and was emplaced in the main asteroid belt at some later point and has just lost that CO2 over time. Based on the dynamics of main belt comets and this particular object, it's more likely that we think that it's more likely that CO2 was never accreted, but we just can't strictly rule that out. So there you have it. This is 238P Reed. It's our main belt comet with a coma of water gas and unusually low CO2 abundance. Thank you.
Okay, any questions in the audience? I have a quick question as well. This is a picture from some other time. How active was the comet when you observed it with JWST? Was it near perihelion?
This is our accompanying YEARCAM observation. Yeah, so it was actually at the same time.
That's an actual picture.
So the data we took was about at its expected peak of activity within a few weeks, probably.
Thanks. Question over here.
Hi, I'm Lori Chu from NASA Ames. And I was just wondering, could it be possible that the CO2 is just really the water ice in a much lower level, or done any sort of modeling of what the structure of the comet is?
Yeah, that's the trick. That's where we can't really say definitively this object never had CO2. We can say that the active region is very CO2 poor to a strong limit. Dina Prielnik has a paper, Prielnik and Rosenberg 2009. So that one does some thermal modeling on particularly El Pizarro, but it's, they're all essentially the same at the first order. And CO2 will be depleted to very high depths, hundreds of meters within 10 million years, some large number of years like that. So it's not that hard to get CO2 out. So again, we can't strictly decide one or the other based on this data alone.
Okay, we have one question online.
Can CO2 ice survive on asteroids in the main belt over the age of the solar system?
Yeah, and that's kind of the similar question. It doesn't appear to be the case. It's just way too long of a time for them to stay.
Well, it would be at some point under the surface stable, right?
Yeah, so since I would say at the kilometer scale, possibly not. It depends on the porosity. The material could still, the energy can still get down to the depth and warm it up enough to percolate that CO2 out. I mean, you have 4 billion years to do it, so.
Okay, let's thank again. The virtual one. Okay, the next talk will be a virtual talk.
You hear us still, or we see you, but your
Yes,
screen.
yeah.
Yeah, that sounds good.
Yeah,
Yeah.
okay.
Perfect.
I'll share my screen. Can you see my slide? All right.
Yep, perfect.
Okay, great. Thanks. Well, thanks a lot for the opportunity to give this talk virtually. I would have preferred to be in Rome with you guys, but so I'll talk to you about observations of LBUP with the JWST, which are quite unique because they are some of the most distant spectroscopic observation of a comet ever performed. So the results I'm going to show here, well, very preliminary, are the result of teamwork by the people mentioned here, and in particular Mike Kelly, who just talked, who's the PI of the program, and Sylvia Protopapa, who worked with me on the spectroscopic data reduction here. So I wanted to first take a step back and look at why we study comets. I'm going to be very brief on that because Mike gave a really good, Mike presented it really well. So as I said, comets are some of the most primitive remnants of the early solar system. And that's why we want to study them, because in their ICs particularly, they retain a lot of information about the conditions that were prevailing early on in the solar system. However, when the comets move close to the Sun, the ices they contain start sublimating, and summary comets gets processed during their orbits around the Sun. So among comets from the Oort cloud, which is at the very edge of the solar system, are thought to be relatively less processed because they are on very long period orbits, meaning that they do less passages close to the Sun. However, even these comets are still processed to some degrees. And so the big questions is to see what in their properties is intrinsic and what's due to evolutionary processes. And in order to do that, we need to observe comets over a range of conditions and distance from the star all over their orbit. And these, the observation of Hale-Bopp that we performed address one of these sort of more extreme conditions, which is a comet that has been passed close to the Sun and then has moved away and is again no longer active, meaning that there's no longer ice sublimation, and what we see is the surface of the comets and not the gas that's surrounding it. So the question we want to answer here is what does an Oort cloud comet look like when it is no longer active, and in particular, what does its surface look like? So for a target, we selected comet C 1995-01 Hale-Bopp. So some of you might remember Hale-Bopp. It was an extremely bright comet visible to the naked eye in around 1996. And one of the reasons Hale-Bopp was so bright is that it's a relatively big comet. So Fernandez et al. Estimated the radius of comet Hale-Bopp of around 37 kilometers compared to more typical comets that usually don't go much above 10 kilometers. So Hale-Bopp was very big, and that meant it was a very, very active comet as well. And so the gas Hale-Bopp produced and its composition was observed over a record range of heliocentric distance for comets, as you can see in the plot there on the right. And so this is one of the most well-studied comets ever. The plot here at the bottom shows comet Hale-Bopp observed at different points in its orbit, and particularly in 2011, from observation with the VLT, Hale-Bopp was no longer active. And what these observations have revealed is that the comet was also had also a very high albedo, so it was relatively bright. And to explain that, one of the hypotheses was that the comet was covered by icy grains. However, from just the images from the VLT, it was impossible to confirm. To do that, we needed spectroscopy. And that's where observation with JWST come into play. Under this program with PI Mike Kelly, we observed Hale-Bopp at 46 AU. And what's very peculiar, and the reason why these observations are unique, is that at that distance, most comets would be too faint to observe, even with JWST. However, Hale-Bopp, being as big as it was, we had this unique chance to observe the surface of an inactive comet on its way out after perihelion passage. And so we had a program with a combination of NIRCam and NIRSPECT data. So the NIRCam data to do astrometry and imaging using filters at about 1.8 and 3.6 microns. And the goal of that was really to refine the astrometry because the comets hadn't been observed for a long time. So we needed to make sure that we knew the orbit of the comet well enough to point at it with the NIRSPEC IFU. But the goal of the NIRCam program was also to make sure that we were covering the water band absorption feature on 3 micron that Mike has showed in the previous talk with sufficient signal to noise ratio. just in case the comet was fainter than expected or the sensitivity was lower than expected and we couldn't reach the expected signal-to-noise ratio with the near-spec IFU. So it was to add some sort of redundancy in our program and making sure we were covering this very important band. Then the second time, after refining the orbit with observation with the near-spec IFU using the prism mode to cover a very large range of wavelength from 0.6 to 5.3 microns. And the goal of these observations was really to characterize the surface of Comet L-Bob. The NIRCam observations were performed in July 2022, so relatively early on. And over there you can see images at 1.8 and 3.6 microns. The preliminary analysis we've done on these data is that there's no clear activity detected from the PSF measurements. However, we need to refine this analysis still. So we measured the brightness of Comet L-Bob and, more importantly, its albedo, and found that it was relatively consistent from these preliminary measurements. We find it's relatively consistent with what was observed in 2011 by Sabo et al. So note within the relatively large error bar, which are due to the unknown rotational state of Comet L-Bob. So we were also able to measure the spectral gradient relatively neutral towards the red. So these observations with NIRCam seem to confirm this very high albedo that had been previously observed. However, we were still left to wonder whether this was due to ice grains on its surface or not. And so that's where the near-spec observations come into play. So please bear in mind that those are still relatively preliminary results. And so the near-spec observations were obtained in October of this year. And so the right part of the image shows Comet L-Bob. So this is a collapsed data cube of near-spec between the wavelengths about 1 and 2 micron over there. So very good. First, very good news is that the comet was detected. It was bright enough. The pointing was just spot on with near-spec, so the orbit has been refined well enough, and we observed it. We had also a DITT pattern, and the pointing was good enough that even during the DITT, the comet didn't go out of the field of view, so the observation went as well as could be expected. And from these, we measured the reflectance spectra of Comet L-Bob. So that means the spectrum of the surface relative to the spectrum of the solar spectrum. And as an analog of the solar spectrum, we use observation of the SNAP2 solar analog performed with the near-spec IFU as well. And so here's the resulting reflectance spectra that we derived. The level of signal that we have is consistent with what we expected. So this is the first great news. And we have sufficient signal-to-noise ratio, even in unbinned data that are showed here, to see an absorption band around 3 micron. That's relatively clear. So what I'm showing here on this slide on the right is observations, models that were run while we were preparing the proposals to simulate the surface of Comet L-Bob, including some water ice grains with different properties, so mostly different sizes. And so you can see there that you have about, in these models, that you have about 3 water absorption bands, water ice absorption band around 1.5 to and around 3 microns. And as you can see there, the relative depth of these water absorption depends on the grain properties. So now if you go to the left part of the slide and compare to what we actually observed once we were on target, the absorption band around 3 micron is present, but we do not see any absorption bands around 1.5 or 2 micron. So we still have to see if, the limits that we can put on the existence of the absorption bands, what we refine the uncertainties. But from these preliminary results, they don't seem to be there. That doesn't mean that there's no water ice, but it means that with the absence of this feature, we can put some constraints on, for example, the size grains that would be possible. Produce a 3-micron band, but no 1.5 and 2 micron bands. So another interesting comparison that I'm showing you here, it's the same reflectance spectrum, but now in red is the reflectance that was measured for 67P, so the target of the Rosetta mission, which we thought was a much more processed comet because it's on a much shorter orbit. It's been around the sun quite a lot. And so what you can see in the spectrum at first look quite similar with the same 3-micron absorption band without 1.5 and 2 micron absorptions. And in the case of 67P, there was no real significant amount of water ice on the surface, and the 3-micron band was attributed to either aliphatic organics, ammonium salts, or amorphous silicates by different authors. And so however, there still seems to be some difference between the band we observe in 67P and in ALBOB in terms of depth and exact width of the band, as you can see in this zoomed version. So I'll just gonna stop here after mentioning the next steps. So we need to refine the data reduction to refine the uncertainties so that we could put meaningful limits on the presence or not of absorption bands on 1.5 and 2 microns, and also match the near-CAM photometry to the near-spec observations. And we also need to do some modeling to constrain the surface properties of LBOB and to see if what we see can be consistent still with water ice on the surface and with a high albedo, or if we need to search for other explanations. So that's something to come. However, what I wanted to just take out of these observations is that we actually, for the first time, managed to observe these without a space mission, the surface of a comet, an inactive comet, after it passed from the sun and at very large distance from the sun. And so that opens new opportunity maybe to observe other comets that might not be just as big, but maybe just a little bit closer to the sun, where we could still have a chance to observe the surface without activity. So that's really open that new opportunity to study cometary surface with JWST. And I'm going to stop here and take questions.
Okay, it's open for questions. I have a quick question. It's just there's in the main asteroid belt, some of the very distant asteroids in the outer main asteroid belt have a known 3-micron feature. I think there's like a Europa group series might have that. Do you think this 3-micron is related to that 3-micron in the main asteroid belt?
It's difficult to say at this stage. It really needs some modeling. It could still be water ice with micron size range, for example. So I think we really need to do more modeling and look at improve the signal if we can, and look at the shape of that band a bit further to see what's the most likely origin for the band.
Okay. Yeah, one question in the audience here.
Very, very nice talk. I was noticing that based on your models and the data, the slope between 2 and 1 microns is different. Does that mean that you guys are seeing a different albedo?
We still, we haven't tried to measure the albedo from the near-spec observation yet, so want to be a bit careful there, particularly since we need to refine things in respect to the flux calibration and everything. But the albedo based off the near-CAM observations is consistent with what was observed before so far. So we still need to do this reconciling and checking between the two data sets. So we haven't really looked at that yet.
Okay, thanks once again. The next talk will also be virtual. Okay.
Can you hear me? I can share my screen.
Yeah, you're sharing.
Can you see my presentation now?
Yes, we can see it. It's not full screen yet, though.
Oh.
There you go.
Okay, it all looks good here. We can hear you. So, yes, we're going to have Pablo Santos Sanz, who's going to talk to us about the ring centaur Turriculo from JWST occultation observations. Go ahead.
Okay, thank you very much for the opportunity to present this talk virtually. I'm going to present the first detection of stellar occultation by a distant solar system minor body from James Webb. I don't know why this is not. Okay, now. Well, everything started in 2014 when I was contacted to lead a James Webb Solar System focus group to study the feasibility to observe stellar occultations from James Webb. The discussion within this focus group crystallized in this paper from 2016, where we studied this possibility to observe stellar occultation by solar system bodies and rings from James Webb. Just to remind you, the stellar occultation technique is a really powerful technique that allows us to obtain high accuracy sizes, shapes, and albedos, also mass densities, if we know the mass of the system. We also can characterize very fine details like satellite, atmospheres, and rings. In the case of James Webb is a really very good suite to characterize atmospheres and also rings. We know that it's possible to detect stellar occultations, predicted stellar occultation from the space, because 2 years ago we detected stellar occultation produced by the Trans-Neptunian Object Quasar from the satellite Cheops. This is the paper published this year by Bruno Morgado et al. And this is one of the figures from the paper, from this paper. You can see in blue the limit of the shadow path of produced by Quasar during the occultation, and in red, this is the trajectory of the satellite of Cheops. In green, you have here where the satellite detects the occultation, and in the upper right panel, you can see the light curve of this occultation. So, yes, it would be possible. What about James Webb? Would it be possible to detect also stellar occultation by TNOs and centaurs from James Webb? The short answer is yes, but this prediction, the prediction of such events visible from James Webb, are really challenging due to the complex motion of the telescope around the Lagrange point. Well, as you know, the telescope is in a chaotic orbit, and we need to correct the orbit from time to time using station-keeping maneuvers. So this means that the orbit is not always the same, and this is challenging for stellar occultation, for prediction and for the observation. Well, in spite of this challenge, we decide to ask for time to observe one of these occultation from James Webb, and finally we got time within the Heidi Hamel GTO time. And well, this is a strategy we have in order to predict and to observe stellar occultation from James Webb. First, we selected 40 of the largest TNOs and centaurs, and we ran on a weekly basis prediction for these objects using Gaia DR2 for the position of the stars up to magnitude 20. We did that on a weekly basis because these station-keeping maneuvers that happen from time to time, and as I said, modify the orbit of James Webb. Then we take a look at the predictions to identify the favorable events, and we refine these events using new astrometry. And then we run again the loop. We update the prediction with this new astrometry and so on. And after all, if we are confident with the prediction, we activate the target of opportunity. Well, it is important to know that this is a non-disruptive target of opportunity. This means that we have to trigger the observation at least 14 days in advance. I want to show you some favorable occultation predictions that we obtain. Well, this is a prediction of occultation by the Trans-Neptunian object Ixion for March of the next year. Well, this plot is a bit different of the usual prediction, usual stellar occultation prediction maps from the ground. You have here in this plot at the center the object itself. This red cross is the uncertainty in the ephemeris of the object that we take from NEMA, and the blue line is the trajectory of James Webb. The different dots mark the different times of the event. These plots were made using SORA tools, as you can see about that, read about that in Gomez Jr. et al. 2022. This is another example of prediction by the TNO TC302 that is for August of the next year. Well, searching different of this stellar occultation, we identify a very favorable one by the Centaur Chariklo for October 18. This is the original prediction using the ephemeris for James Webb for August 19. You can see, well, I haven't said, but Chariklo is the first non-planetary object around we detected rings by means of stellar occultation. So you can see here that it's a really very favorable prediction because we can record the main body and also the rings. Also, it's a very slow occultation. This means that we can obtain high spatial resolution, and also the occulted star is very bright. So what we did, we update this prediction using the updated ephemeris to take into account these station keeping maneuvers. This is, for instance, a prediction for September 18. You can see that due to these station keeping maneuvers, the trajectory of James Webb has moved a bit to the south. This is good for us. Then this is September 23. Well, here regarding September 18, there is only a slight change in the theming of the occultation, and this is for September 27. Well, as we trust in this prediction, and the error in the ephemeris of the object is really small, it's around 3 milliseconds, we decide to activate the target of opportunity. Okay, and of course we continue updating the maps, the predictions. When we update in October 12, we see that due to the station keeping maneuver, the trajectory of James Webb moved to the north. This means that in this case we only detect the rings of Chariklo. Well, we have triggered the target of opportunity, so we can't do nothing. Just wait and cross our fingers and wait for a good detection. This was the prediction that we did for the same day of the occultation, very similar to the previous one. And well, here I showed you the observation details of this occultation. You have there the Gaia Deer 3 ID of the occulted star. Also, we use NIRCam and the filters, these two filters at 1.5 and 3.2 microns. The idea is to, with these filters, with these choices, to maximize the flux from the occulted star while minimizing the reflected flux from Chariklo itself. We observe with a cadence of 3.3 Earth. This mean a resolution at the plane of the sky where Cariclo and the rings are of around 750 meters. Well, the time is really very short, as you can see. And at the end, we obtain a total of around 15,000 images during the observing time that was more than 1 hour. Well, and this is a video and animation that we did using the NIRCam data at 1.5 microns. You can see, well, the moving object is Cariclo, and at the center of the image is the occulted star. Well, apparently, Cariclo is passing very close to the occulted star, but of course, one needs to analyze the data, to do the photometry in order to see if the occultation happened or not. Well, in the next slide, I can tell you that finally we detected the rings using NIRCam at both wavelengths. And in the left panel, well, you see the prediction, and you can see in the right panel the preliminary light curve at 1.5 microns. And well, the first drop corresponds to the first part of the ring, and the second drop to the second part. We didn't detect in this preliminary light curve the main body. And well, taking into account this distance that is around 700 kilometers, our prediction was a really, really good prediction. We are searching for, of course, in the data we are searching in the images for new putative rings, and also we will do a depth search, a depth look for new satellites or new dusty and diffuse rings. Well, I will finish my talk saying that the detection, the prediction and the detection of this occultation is a promising omen for future events. And of course, we will ask for time to observe more events produced by other TNOs and centaurs in the following opportunity. And that's all. Thank you very much.
Okay, this is open for questions. I have a quick question. That last slide you showed was really dramatic. And if there was any material exchange between the body and the rings, such as an atmosphere or exosphere or something, you probably would have noticed something there, right? So there's basically, it looks like there's no material between the rings and the body.
Can you repeat the question, because I have problems to understand?
Yeah, on this last image, there's no atmosphere or anything from the main body, right? If there was an atmosphere, would you expect to have detected something?
Yes, well, in fact, this is the prediction, but the post-diction, we were really closer to the main body. But, well, in principle, we haven't detected nothing like an atmosphere by now, but as I said, this is only preliminary, so we need to refine the photometry and to take a deep look in order to see if there is something more. Maybe I don't know if atmosphere, no, but perhaps some diffraction pattern if we are closer to the main body. But well, nothing by now. We haven't detected nothing, but in the future perhaps we can say something about that.
Okay, and we have one question online.
That may be a very similar question. What can you expect from two-color observations about the composition/grain size of the rings? Also, do you see structures in the rings?
Yes, we see some structure in the rings, and of course the idea to observe using two wavelengths is to obtain a constriction on the size of the ring particles. So yes, we are starting to work on this direction.
Okay, thank you. Okay, our next talk will be from the auditorium here. And It'll be given by Geronimo Villanueva about astrobiology with JWST, searching for life and habitability in our solar system. And Heidi Hamill has something to say.
So you've heard reference in several different talks to Heidi Hamill's observations, and Geronimo very graciously allowed me 2 minutes to tell you what they are. In this slide, you can see JWST between the Earth and Mars, and that red region, it shows you what is excluded in the solar system. So Venus, Mercury, Earth's moon, the sun, all are excluded, but everything else from near Earth objects all the way out to the edge of the solar system is visible to James Webb Space Telescope. And so as part of my guaranteed time observations as an interdisciplinary scientist for JWST, I crafted a program that allowed us to see all of these things. And it wasn't done by me. It was done by this fantastic team of people. I'm not at the top. I'm at the bottom because these folks have done all the work. And I especially want to call out Stephanie Milam, who has been my right-hand person for 10 years now to ensure all these observations across the solar system were able to be done. And you've heard already about some of these things. Jane showed you some DART. You already heard about occultations. You heard about other observations. Mike Kelly showed you some spectroscopy of comets, and there's much more. And so I do have a poster that was based on something that Klaus Pontoppidan put together, but I'm happy to answer any questions about any solar system objects that you didn't hear discussed today and tell you what their disposition is. So thank you for that time, Geronimo, and now let's hear from Geronimo.
Yes. Thank you, Heidi. Yes. So I'm going to be talking about, so as Heidi was saying, she was the inspiring, she invited all of us to do a great science with this. And in this case, we're going to be talking about the Mars Oceans Worlds GTO, Guaranteed Time Observations, and we're going to be focusing on Enceladus, Europa, and Mars. So let's start with Mars. So we did an initial image release in September. The data was taken actually, I think we got the data on the 5th, and then the data was already pre-analyzed already on the 9th. So in a record time of 4 days, we already got some ideas what was in the data. But the data is challenging. Actually, when we were invited to work on Mars, we knew there's going to be a challenge because Mars is too bright. So this is some of the first data that we got from NIRCam. You can see the upper one is the 2.1, the short wavelength filter, and then the 4.3. You can see they look like a stamp because we need to avoid saturation. Mars is probably one of the brightest objects out there, and it's broad, standard, so it really was challenging. And one of the main fears you can see when you look at the 4.3 is look at this white or yellowish color. So you're worried about saturation. And indeed, we are very close to saturation, but unfortunately for Mars, all that flat flux is real. Mars has a very flat flux of 4.3, mainly because the temperature is very homogeneous there. The surprise was when we got to Hellas, which is the deepest point on Mars, we were expecting higher temperatures being deeper on Mars, being warmer there. We were expecting a warmer, brighter color. We saw a darker color. So again, fears of saturation, is this real or not? And is this actually real? And we're actually seeing surface pressure on Mars. And I wanted to show here, just to quickly, what it means. So this is spectrum, synthetic spectrum on Mars in the 6 millibars and 10 millibars, and the filter is in green. As you can see, as you go to higher pressures, 10 millibars at the deeper the basin, the flux drops, mainly because there's a lot of CO2 absorbing all that flux. So that drop in flux that you see in the filter is introduced by having a bigger column of CO2. So it's real. That decrease is a real feature. And again, it shows the power of the data, just a quick analysis. This was done for the press release. But I think, I'm in spectroscopy, so I think the most interest for me was in this spectrum. This is just, we did a quick analysis on it. And it shows the plethora of spectral features. I think, you can see in one snapshot, we can get all this about Mars. We can map all these on Mars. And we have a lot of spacecraft on Mars, but we don't have a lot of instruments that can do the full disk of 3,000 resolving power in this wavelength range. So this is definitely a unique asset for us. And you can see the CO2 features. You can see the water features. You can see that those features, strong water features. We see this 3.3 thing, which is known on Mars for surface features. And then you see carbon monoxide and a lot of CO2. So, I mean, you can see all the features we're expecting, but, one of the things we're working for is, we have 3,000 resolving power. So it's a lot of things that we're going to go deeper into the spectrum. The challenge with Mars is that it saturates. This is a paper when we prepare all this in 2016. This shows the different wavelengths. These are images of Mars at different wavelengths with the spectrometer, James per R second square. You can see we're saturating in a lot of places. This is a whitish color, you can see. So we have to be careful where in which spectral area we can do science. But fortunately, the 3.3 micron is pretty clear, and this is the key thing. What do we care about 3.3? Well, 3.3 is great because it can measure water, D over H, but also methane. Methane is we consider typically a biomarker of Mars, or indicator of activity. It could be an indication of biology or geology coming from the subsurface. We have detected it from ground, very difficult measurements, so it's controversial. There is orbiters that we have on Mars looking for it, and then we have rovers measuring. So what can JWST provide to this? So this is an image, a paper that we just published recently in 2020, and it shows here latitude in the x-axis and then altitude. And you can see these are solar occultation that we can do from orbit on Mars today. But you can see we can only do measurements above 20 kilometers typically because we are only tangentially measuring the atmosphere. We actually have a void in the equatorial latitudes. So we never see it, and we get very sensitive upper limits. The color is the sensitivity of the upper limits. So Curiosity, which is really in the middle, in the wrong point for our measurements, is detecting methane, and they see plumes up to 10 ppb and 1 ppb at background level. So the good thing about JWST can do the full column. It will penetrate the whole atmosphere, and it will allow you to get measurements across the whole latitude range and to get a very sensitive upper limit. That's why JWST provides a new way to do things that you cannot do from orbit or from ground there. And what do we expect? This is another simulation. You may get a very bright feature there, the red feature there. You can also look for other organics. So this spectrum, this is a true simulation that you can do. You can actually identify all these features. The challenge is you need to be super bright because the solar feature is also very bright. So I will say one thing about this. We got 15 seconds of integration, so which is one of the incredible. You can do all these things with 15 seconds. We have not detected methane yet, and we got limits. The limits that we have right now are contradicting previous claims, so this is important. I think it's great. And we also saw a lot of surprises that we're working on the paper about that. So we put the little thing not to share, please. We have other things I'm going to show in the talk, so not share these things. But let's go to Europa now. Again, they're all related to me in my science because of the molecular signatures. I'm looking for the same signatures of water, the soup of life, the organics, and things like that. So what we can do? So this is a nice simulation we prepare for what we expect with Europa. So if you put the IFU mode, the gradient mode, and do high-resolution spectroscopy, and if you have the plume that has been shown to be there, you can actually map it. Europa is 1 hour second. You can actually get a spaxel, and you can actually look for all these molecules in the 2.5 to 5 micron. And we have models for all these features. We can look for water, the organics, carbon dioxide. So we can do now spectroscopy. We don't only looking for continuous signatures of plumes. We can actually know the composition of those plumes. So for us, it's a big interest on this thing, and we can actually get a definitive detection of all these things. And there were claims about, the image here is actually a claim of the detection of plume with JWST, with Hubble. So we took data. The data was taken 10 days ago, so this is really, really recent data. And we're working very diligent because it's very high impactful for programmatics and NASA. So this is an image of 2 microns. This is the IFU data, actually the NIRSPEC data, just a slice at a particular wavelength. We can see the brightness feature and the right point. There's some morphology. We're trying to understand if it's real or not. But the thing that we discovered, again, this is a new thing. We saw this huge feature at 2.7 microns, and then we saw 4.3. We were wondering, we were never seen before. It was a new feature, and it's definitely carbon dioxide ice, which is very novel detection on the surface of Europa. And it has a lot of implications of the chemical diversity of the surface of Europa. So I think this is a big thing. We're working on timely a paper with the GTO team to make this public. And the beautiful thing about that detection is not everywhere. It's actually localized in a very specific place on Europa, in the Tara region. So we can actually map it. You know, the features that you can saw, they were pretty generous in size. So we can map this very nicely across the planet. So this is a beautiful data set. And again, this is only a few minutes, which is amazing what JWST can do. So we have several neon features. I just showed you two. There are several other ones also. We have no signature of plume yet. And we have an upper limit, which again is challenging previous claims, so I think it's important. We're trying to verify this. And we have other surprises too, so we're working on a paper on this. And, okay, I'm gonna move now to Enceladus, the last component here. We saw a huge plume, and I'm gonna go quickly to the point on this. I was pretty surprised about this data, I must say. So this is what we saw. This is amazing. I mean, this is the spectrum at, this is the value of Harvard solvent power. This is never seen before at this resolution. You can see all these water features. These are all real water features of Mars. Enceladus, right? The green features the model of the continuum. The absorptions are solar lines, actually, because we're looking at reflected sunlight. But you can see all these features. You can actually do a rotational study on this, and you can know that these are cryogenic temperatures, very low temperatures. And from the intensity of the lines, you can actually start mapping the plume and see where it is. So we knew Enceladus had an activity. This is an artistic simulation, but we knew there are activity in Enceladus. We know Cassini have taken data, but we didn't know where was it. There was some idea there was a big extended. We knew some of that water was going, but we'd never seen it before. So this is an impressive image taken with James Webb. It's only a few minutes on Enceladus, and you can see that blue thing is all real. This is just a water emission. This is not. There are no continuum here. There is no map, ICES. This is real water emission. You can see the huge plume. We can actually develop a little model of where the plume is, and you can actually map it to the tiger stripes. The tiger stripes is the warmer thermal part of the South Pole. So we know they come from the south. This is a Cassini image. You can see this is an image of the continuum, and you can then see if you stand it to 40 times the radius of Enceladus, you can see this huge plume. So this impacts a lot because this water doesn't stay near Enceladus. It's an exosphere. This is going to spread water all across the Saturnian system. So it's a big source of water. And we're now looking for the other molecules. So we are now looking for the other organics that should be there. So, which is amazing. And then we only have a few minutes of integration. Again, imagine if you do it 1 hour, you can go deep and do other, it's pretty astronomical. The contrast to the continuum is also huge. And we also know the temperature and the composition, which is nice. We have a good excitation model for this. And we have other ice features and detections which are very interesting. So I think many more discoveries. If you want to interested in the data, please talk to us and we can help you. And all the retrievals are done with a tool, our open tool too. So we wrote a book about it. So if you want to learn more how to do all this, please let us know. Okay, thank you.
Okay, thanks. Great talk. Any questions? Okay, we'll go online first.
Is the plume located near the location of other observed plumes on the South Pole? Does JWST tell us anything new?
Yes. So let me show this map. So this is the location of the emissions. So they are related to this is related to the known location of the plume. The previous idea of the plume, you can see that is a continuum map. There's not a map of water before. There were some flybys that there were mass spec measurements, but we didn't know what the plume is made. We can measure so we can measure methane, for example, with high accuracy, CO2 and CO, and we can derive abundance ratios or upper limits about those species with higher certainty. And this is what we are reporting. We're going to be reporting in the paper, yeah.
Okay, and question? Right there.
Hi, Chris Wanchek. I'm a science author. Fabulous. And any speculation on what you might be able to see on Titan?
Well, so, you may have seen there is a paper, actually, Connor Nixon is here, the lead of the Titan team, And we saw the press release last week. It's extraordinary what they have achieved. They can go deep through the clouds. And I think I will recommend you talk to Connor more about the Titan results. There's a poster right there.
Okay, our next talk will be by Ian Wong about Kuiper Belt science with JWST. Yeah. And just a reminder that we'll take, after this talk, we'll take a picture here in the auditorium. And I guess people online could be part of that as well, right? So stay online as well.
Turned on down here.
All right. Close your pointer here. Okay. All right. So I'm the last thing keeping you from break, so I'll try to go quickly. All right. So what is the Kuiper Belt? So beyond the orbit of Neptune is this large population of primitive icy bodies that are reminders from the remnants from the era of planet formation. Over 3 decades of observations have revealed a highly dynamic structure, as well as an astounding diversity in the types of surface properties. So better knowledge of the chemical and physical nature of these objects will surely give us, revolutionize our understanding of early solar system formation and evolution. During the first year of JWST science observations, about 90 hours were awarded to 6 different GTO programs targeting 26 TNOs with 3 different instruments. To this is a companion GEO program that will observe an additional 59 targets with the NIRSpec IFU mode. Some of the notable targets for the GTO program include the 10 largest TNOs, members of the Haumea collisional family, and centaurs, including Chariklo, which you just heard about from Pablo. So the sampling of objects in this combined program will sample all the dynamical classes that are tested in the Kuiper Belt. So in this talk, I'll give a sort of a whirlwind tour through some of the notable highlights so far from the GTO observations, with a focus on the NIRSpec IFU observations. Starting out with this pair of high-resolution spectra of Pluto and Charon, you see in the IFU collapsed cube that they are nicely resolved. In addition to the exquisite signal-to-noise of these spectra and the plethora of absorption bands, one can clearly see the stark contrast between these 2 binary components. Pluto is the most well-studied of the TNOs to date and provides an excellent demonstration of the capabilities of JWST in Kuiper Belt science. Here in the upper right, I have a zoomed-in version of the high-resolution JWST NIRSpec spectrum, short order of 2.5 microns. In just over 30 minutes of exposure time across the 3 gratings, JWST delivered precision that rivals the combined spectrum below, which is from over 12 years of ground-based data. While nitrogen is a predominant species on the surface, nitrogen ice, methane is the dominant feature in the spectrum because it is much more spectrally active. And therefore, nitrogen ice is only attested by that small feature at 2.15 microns. In addition, we see clear detections of CO and ethane, the latter of which was only previously attested from flyby observations from the New Horizons spacecraft. Speaking of New Horizons, the flyby observations revealed a very inhomogeneous surface, and this JWST spectrum is the first of 4 that will combine to provide full longitudinal coverage of the Pluto surface. Incidentally, this observation here was taken at almost the opposite viewing geometry to the New Horizons flyby, thereby providing our first high-quality spectrum of that opposite hemisphere. Charon, on the other hand, does not have methane ice features. Instead, has a spectrum dominated by water ice. In particular, at 1.65 microns, we have this crystalline water ice feature, as well as a Fresnel reflection peak at 3.1 microns. These were all previously seen before. Now, these smaller features at 2 and 2.2 microns have been attributed to ammoniated species on the surface, and were previously only attested in localized regions on Pluto's surface. This is from an opposite viewing geometry, so this suggests that ammoniated species are more widespread across Pluto's surface. What's really notable about the spectrum is that it provides the very first robust detection of CO2 ice on the surface of Charon, which are manifested here by this narrow feature at 2.7 and the 4.25 band. Moving now to Eris, we find basically a textbook methane ice absorption spectrum. If you look at these long wavelength absorption features beyond 4 microns, the strength of those features suggests that they are enhanced by the singly deuterated isotopic form of methane, CH3D. Another possible contributor at 4.55 microns are nitrile species, a hypothesis that's supported by the tentative detection of nitrogen ice between 4 and 4.2 microns. Rounding out the dwarf planets are 2002 MS4, Silesia, Gongong, and Sedna. These objects are too small to retain significant methane ice on their surfaces. Instead, we see very Charon-like spectra with water ice throughout. 2002 MS4 and Silesia are very similar. They both show this prominent Fresnel reflection peak indicative of crystalline water ice, as well as a prominent CO2 ice feature at 4.25 microns. Meanwhile, Gongong and Sedna are very red throughout the J-band region, with very little hints of any crystalline water ice. Instead, what we find actually are hints of methanol absorption at around 2.3 microns, as well as strong evidence for aliphatic carbon by virtue of this dip around 3.4 microns. In addition, we have a cluster of features marked in red that are indicative of, possibly indicative of ethane ice. So for a clearer view of this, here's an inset of Gongong spectrum in this wavelength range, alongside laboratory spectra of aliphatic organics and ethane ice. And here you can note the correspondence in some of the spectral features that support this detection. All right, so before I dive into the Haumea family, a quick introduction. Haumea family is the only identified collisional family in the KBO population. And its confirmed members are notable in having neutral optical colors as well as high water ice abundance on the surface. Looking more broadly in dynamical space, there are dozens of other objects that are in the vicinity of Haumea, and they don't show the notable water features that the confirmed members have shown. So the question arises as whether those other objects are just simply background objects in the TNO population, or instead form a subclass, a distinct subclass within the broader Haumea family. So following this, as part of the GTO program, 4 objects from each of those classes were observed in low resolution mode. Haumea itself will be observed in the upcoming months. So stay tuned for that. All right, starting out with the high water features, high water Haumea family members. True to form, they have very, very spectacular water ice features in the near infrared. And notably, each of them individually shows an exquisite 1.65 micron crystalline ice absorption. And here's another opportunity to just really to showcase the immense leap in spectroscopic quality offered by JWST. Here are some ground-based observations of the same 4 objects, where you see the quality is just not comparable. Now, finishing off with the low water Haumea family members, they all share across the board red spectral slopes in the shortward of 1.5 microns, as well as no or weak hints of any crystalline water ice features at 1.5 and 2 microns. Notably, the bottom 2 spectra show evidence for strong evidence for methanol absorption at 2.27 microns, and all 4 show very strong CO features at beyond 4.5 microns. Now, probably the most interesting feature of these spectra is the saturated CO2 primary band here. For the middle 2 spectrum, this actually shows a very interesting, unusual edge feature that manifests as reflection peaks. And this type of feature has never been seen before on a planetary surface. And we are still kind of working towards interpreting what that might be. But an early hypothesis that this is a geometric effect due to the transition between volumetric and surface scattering. There's so much CO2 on these middle two spectra that we also see the overtones bands between 2.6 and 2.8 microns. And besides that, there are also hints of aliphatic organics, as we saw before on some other spectra, particularly in 2002 AW197 here. So here's a zoomed-in view of the middle two spectra, where you can appreciate this very unusual CO2 primary band, as well as the overtone absorptions. In addition, we have a very strong, robust detection of the 13 CO2, the heavier isotopic form, as well as tentative detections of a band that is attributed to 12C18O2. Together, modeling these, we can actually get novel constraints on the isotopic ratios of carbon and oxygen, which have fundamental implications for the cosmochemistry of the outer protoplanetary disk. In addition, we have a range of possible detections of sulfur-bearing species, and if confirmed, this would be the very first robust confirmation of sulfur chemistry on the surface of a TNO. All right, so I'm just going to finish up real quickly with some forward-looking remarks. This is still ongoing work. I kind of missed out on splashing like a big embargoed or preliminary, so please don't share these. So we're continuing to improve our data analysis frameworks as we await final absolute flux calibration for NIRSpec. On the spectral modeling side, the greater wavelength coverage offered by JWST, as well as this huge repertoire of new detections never before seen of various absorption bands, will certainly challenge existing modeling frameworks, and we expect there to be a lot of chemical and physical considerations that need to be considered for the first time, as well as good motivation for future laboratory studies of analog species at low temperatures. Looking more broadly, we are going to have a growing treasure trove of these high fidelity, high quality JWST spectra for a wide range of TNOs, and this will enable population level studies that may uncover underlying aspects of solar system formation and evolution. Before I end, I want to thank, this is a huge collaborative team effort, as it's a common theme this week. I would like to give a shout out to the 6 PIs of the GTO programs, as well as a large team of co-Is and collaborators that made this work possible. So thank you.
Okay, thanks. Amazing observations there. Before we go to questions, I'll just have a question about, so the Haumea family, there are different types of Haumea family members. Do we know why there would be different compositions? Some might be more interior from the Haumea, or why would they have different compositions?
Yeah, so the high water objects are certainly confirmed to be Haumea family members that are most tightly dynamically bound in proper element space. But there's kind of a lenient, if you have a more lenient definition of where the Haumea family extends to, then you have these objects like the ones that are shown with very, very strong CO2 ice features. Whether or not those are a subclass in and of themselves, distinct from the background, remains to be seen. So from the GEO program, there's going to be a lot of these other objects that are certainly not Haumea family members.
So there's a correlation between the closeness to Haumea and water ice then, correct?
Yeah, so the tightest ones appear, the most robustly confirmed members are the ones that have those water ice features. So.
Okay, thanks. We got a question in the back.
Akiba Burj, Goddard. Thank you for the talk. So in passing, you said something about with the dwarf planets, they were too small to hold methane ice. Could you elaborate on that?
Yeah, so methane ice is highly volatile. So even at the cold temperatures of many of the Kuiper Belt objects, it would be depleted on the surface over the course of the solar system history. So the only reason we think Pluto and Eris have retained it is because of a vapor pressure controlled atmosphere. So it's being maintained in this atmosphere and recycled.
A follow-up to that, Sedna is that a borderline case where you expect methane, or you wouldn't expect methane on Sedna?
I think it's a borderline case. I have to check. So there's a Shaler and Brown kind of the vapor pressure sort of escape framework, and I believe Sedna is kind of borderline, as is Haumea.
Okay, thanks. Any further questions? We have one online.
Can you tell the difference between crystalline and amorphous water ice on the surface of these objects via JWST spectroscopy?
Yeah, so I mentioned there were these two features, one's at 1.65 You have a Fresnel reflection peak at 3.1. So both of these are predominantly due to the lattice structure of crystalline water ice. So by modeling this, which is still a work in progress, we can constrain the amorphous and crystalline fraction. There are, of course, grain size effects and all of complicated physics, but yeah, the short answer is yes.
Okay, let's thank all the speakers again. Very on time, very good speaking.
Okay, before you run away, both online and in person, we're going to do a conference photo. So if you're online, please turn on your camera if you can. That would be great. We're going to project you up on this screen. And if you're in person, we're going to try and get you to stand in front of this screen. So if you can all come down here and put taller people towards the back. So we're going to take the photo from this side. Taller in the back, shorter in the front. And Thomas is going to take the photo for us. Very kindly offered.
We're seeing your photos online, so thank you for turning on your cameras.
All right. And the quicker you come down here, the quicker you can go for coffee.
Nicely said. I just stand behind you. I think so.
What is this?
Keep moving towards the front.
I always hide in pictures, actually.
I wanted everybody
not actually there.
like if they wanted everybody online to turn their things on, then we all pile in front of the screen so you can't see 2/3 of them.
Well, so you can only get like 20 people on the screen.
Yeah.
They're all a copy of each one.
Not gonna have our masks on. They're still gonna tell us all to smile.
Don't breathe. Did you breathe it? Breathe, Eddie?
Okay, you can all go for coffee now.
Thank you, Thomas. Thank you.
Thomas.